everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm going to deal with the course Computational Aerodynamics. And today's topic we will be seeing finite difference and finite volume approach. Before that, let's recap what we have done in the previous modules. So we had seen what is computational fluid dynamics and why it is beneficiary when it is compared to the experimental and theoretical approach. And we had seen what are the steps involved in the fluid flow problem. So first we need to identify what is the fluid flow problem, then physics of the fluid, then which type of equations we'll be using, whether the flow is compressible or incompressible, or heat transfer problem. So those equations has to be used. Then we need to discretize those equations. So which type of, then we'll be seeing which type of grid we'll be using. So then we'll going for the solver and the simulation results. And these are the governing equations which we had seen. So continuity, momentum and energy equation. And we had seen some examples. So external flow, this is the flow over wind turbine. And then we have the internal flow phenomena. So this is a mixer velocity plot. And we had seen there are different types of approach we have. So one is Eulerian approach, other one is the Lagrangian approach. So as I told you, so the Lagrangian approach is all about tracking of individual fluid particle, and the Eulerian approach is about the average of particular cross section. So you need to know the fluid properties, which are like U velocity, V velocity, W velocity, pressure, density. So these values are taken for an average quantity with respect to space. So if you are measuring these fluid flow properties, velocity and temperature of a single fluid particle, then we are said to be like taking the Lagrangian approach. So, and we had seen the structured grid. So there are different types of grid. So structured grid and unstructured grid. So we had seen like what is structured grid and what are the different boundaries we have. So left boundary, bottom, right and the top boundary. So what are the boundary conditions that we can apply here. And we have seen the basic entities of this domain. So as I told you, like domain is nothing but it's a circumference of this entity, and inside the domain you have subdomains. So you can see different cells of a quadrilateral shape. Okay, so if the spacing between these two grid points, so the grid points are nothing but, so the intersection of the x lines and the y lines is nothing but, this is called the grid point. Okay, so if the spacing, so let's see the zoomed view. So if the spacing between these two grid points, so this is, let's say 1, 2, 3 and 4. So let's take this as delta x1. So this is delta x2 and this is delta x3. So the spacing between this x1, delta x1, delta x2, delta x3, if this delta x1 is equal to delta x2 is equal to delta x3, then this sort of grid is called a uniform grid. Okay, so this uniform grid can be applied like with x direction and in the y direction also. Fine. Now whether the uniform grid is applicable for all the fluid flow problems or not also we have seen. So it is not mandatory that you need to have only uniform grid. So depending upon the type of problem that you have, so you can vary the spacing of the grid. So this is what we had seen. So here you can see that the spacing along x axis is being changed, but the spacing along y axis is unchanged. The meaning is, so the grid point distance, so the delta y1 is equal to delta y2 is equal to delta y3. So if you take this one, so the y distance of the grid points are equal, but the x distances, so let's take this is one grid point and this is another one. So let's take this is one set of grid point, this is another set of grid point. So let's take this one and this one. So let's take this as delta x1, this one as delta x2 and this one as delta x3. So these are not all equal actually. Why? Because the spacing is not same. Okay, so this sort of grid is called the non-uniform grid, and this non-uniform grid along y-axis also we had seen. So in this case, what we had, so what we have like delta x1 is equal to delta x2 is equal to delta x3, but so along y-axis, so the spacing is not same actually. Okay, so therefore delta y1 is not equal to delta y2 is not equal to delta y3. So this is what we have if we have non-uniform grid along y-axis. So you can vary independently the spacing of the grid along x-axis and y-axis, and you can vary both the spacings at a time also. So here the non-uniform grid along x-axis and y-axis. Okay, so this sort of region, so whatever we are seeing is called cluster region or the finer region. So it's like, so you can see the darker region here near to the boundaries. Okay, so here you can see the near to the boundaries you have a darker region. So basically this sort of region is called the finer region. So where you have more number of grid points with the less grid spacing actually. Okay, so mesh spacing or the grid spacing, the meaning of mesh spacing or the grid spacing is nothing but the distance between two grid points. Okay, so the grid, since we are talking about only 2D mesh, so if it is of 3D, so you will have delta z also. So basically delta x, delta y, and delta z. So this is spacing along x, and similarly this is along y, similarly this is along z. Okay, grid spacing along x, grid spacing along y, grid spacing along z direction. Fine. If it is very close, and if you have more number of points near to the wall, or let's say this region, certain region, so then this sort of phenomena is called the finer region, and the other, this region you can see, so this is called the coarser region. So you have less number of points and with more spacing. So if you have less spacing, then you have the phenomena called finer region. If you have more spacing, then you have a phenomena called coarser region. Okay, and I have a question like, why do we need to use finer region and why do we need to use the coarser region? Okay, so think about that. And so here I can explain like there is one more kind of thing. So you have coarser grid and finer grid. Okay, so as I told you, so you need to see what are the minimum number of grid points that can be used to get an accurate solution. So let's say you will have an experimental value and you will have numerical value. Okay, so numerical value is coming from CFD, experimental value is coming from an experimental setup. Okay, so let's say the flow over flat plate, let's say at certain point the velocity is 1.45. So you need to check at different grid points. Let's say for initial you have taken 1 million cells of grids. Okay, so 1 million grid points, so 1 million grid points and 2 million grid points. Okay, so here these things, at what number of grid points you get an accurate solution or the approximate solution near to the experimental value has to be estimated and need to be used. Let's say you have one more 3 million also. So for 1 million, if you have let's say 1.39, for 2 million if you have 1.448, for 3 million let's say you have 1.449. So it is sufficient that you use 2 million grid points so that your value is near to the experimental value, and you can reduce the computation cost and the time, okay, to solve the fluid flow problem. Fine, so this is called the grid independency study or it is called mesh independence study. It is very important. Okay, and we had seen what is unstructured grid also. So here you can see this cell is of triangular section. You can see here you have the triangular section for unstructured grid, whereas for structured grid you have the quadrilateral cell actually. So this is of 2D. So in 3D that would be, so here if you see a triangle, then you will get a tetrahedron. Okay, and here what you get is hexahedra actually. Okay, so this is what you have. This is 3D cell, 3D mesh cell, and this is for a structured grid, and this is for unstructured grid, a 3D mesh cell. Okay, so here the difference between the structured grid and unstructured grid is like, so the structured grid can be applied for a simple and regular objects where the boundary is confined or defined, but whereas for unstructured grid, the application of these aspects would be beneficiary for only a complex problems. So you cannot use this unstructured use we can use, but you cannot use. Why? Because if you use this one, your computation cost will be higher. Okay, and the complexity of modeling equations also would be higher. We recommend that if you are having a simple fluid flow problem, let's say floor, flat plate, simple geometries, you can use a structured grid. But for a complex problems or irregular objects or a complex domains, so you can go for unstructured grid. So why? Because as I told you, so if you have, let's say, 10 grid points, you need to solve 30 equations. Okay, so the meaning is like at each and every grid point you should solve 3 equations. If you have 10 grid points, you should use 30 equations. If you have 100 grid points, you need to solve 300 equations. If you have 1 million grid points, you should solve 3 million equations, let's say. Okay, so when you compare structured grid and unstructured grid, for unstructured grid, so you will have more number of grid points compared to structured, and the complexity level would be somewhat higher, and the computational time would be higher. Okay, so depending upon the problem, you need to choose whether you need to go for structured grid or unstructured grid. Okay, and as I told you, so why we need to use a coarser mesh at some points and finer mesh other points, we can see an example here. I think you know the concept of boundary layer. Okay, so here if you see, this is of airfoil shape. So here you have a boundary layer actually. So the meaning of boundary layer is a layer which is adjacent or which is near to the wall or the body because of viscous phenomena. So it is a viscous layer which is present near to the body. So what is happening is like a fluid which is coming and passing over this object. The first layer of the fluid will stick on this body. Okay, so this sort of condition is called the no slip condition. Okay, so the no slip condition means the fluid layer, the first fluid layer which is coming and passing over the object, so will stick to the body because of viscous phenomena. Then that sort of thing is called so no slip condition. So because of no slip condition, the first fluid layer will have the zero velocity. So velocity is zero at the wall for a fluid particle. But another fluid layer which is coming and passing over the first layer will try to drag the first fluid layer. So let's say this is fluid layer 2 and this is fluid layer 1. So this fluid layer 2 will try to drag fluid layer 1, and what is happening? It's like the retardation. The velocity will be reduced for second fluid layer. Okay, so this is what we have. Let's say, so the first fluid layer will have zero velocity. So second fluid layer will have some velocity, and similarly the fluid velocity will keep on increasing till the free stream. Okay, so this is the basic profile for the boundary layer. Okay, so inside the boundary layer, the flow is said to be viscous. So the outside the boundary layer, the flow is said to be inviscid actually. So you have two types of like equations, like you have the viscous equations and you have inviscid equations. So that thing you can see here itself. So when you see the governing equation here, so for the momentum equation, so if the flow is said to be inviscid, so this term will be cancelled. Okay, if the flow is said to be viscous, we need to take the shear stress term actually. Okay, so why we are seeing these two aspects is because, so when you use inviscid theory, out of the boundary layer where you have so many number of grid points, which is a part of the body. So we have so many number of grid points. If you are using the inviscid theory equations, so the complexity level will decrease and number of equations that you need to be will be same, but the term will reduce. Actually, the viscous terms will reduce, and you can simplify equations very well. But in the viscous region, you should take heat transfer into account. You should solve the energy equation. You should take the shear stress term, and therefore you should take special treatment in the viscous layer. Okay, so therefore the boundary layer will separate the viscous region and inviscid region in the flow. So therefore, what is happening in the inviscid region? If you use the coarser mesh, that would be sufficient. Why? Because we are very interested what is happening near to the wall. Okay, what are the effects that is happening? Let's say if you are checking the temperature distribution over the thermal, okay, phenomena over the turbine blade, if you need to see what is the heat distribution due to conduction convection in the blade, so you are very much interested at this area. Okay, so therefore more number of grid points has to be used near to the wall, and less, you can use less number of grid points away from the wall, so that is called coarser mesh. So therefore you need to see, depending upon the application, at what point you should use the coarser mesh and at what point you should use finer mesh. That is very, very important. Fine. So one more thing, the boundary layer, whatever the phenomena we have, so the delta, so the thickness of the boundary layer is actually inversely proportional to the, we have an approximation actually. So it's like 5 divided by delta Re, something like that, some constant, let's say 1 divided by delta Re. So here the meaning is, as the Reynolds number is increasing, so I think you know what is Reynolds number. Reynolds number is nothing but rho V L by mu. So rho is nothing but the density of the fluid, and V is nothing but the reference velocity, and L is nothing but the reference length, and mu is nothing but the dynamic viscosity of the fluid. Okay, so as the Reynolds number is increasing, so the boundary layer thickness will decrease. So here you can see the Reynolds number can be increased in two ways. So either you decrease the dynamic viscosity, or you can increase the velocity. Given the density of the fluid is constant, you can increase its velocity, or you can increase the reference length. Fine. So if you are increasing the velocity, automatically the Reynolds number can be increased. So therefore, what is happening at high speeds, at high velocities, the boundary layer thickness will decrease. The meaning is like, so the boundary layer will become shorter, shorter, and so much shorter. So therefore, what you need to do, you need to actually perform a very, very, very finer mesh near to the wall to capture the boundary layer. Okay, so let's say you have a mesh like this near to the wall. So this is wall, let's say. So if the boundary layer is like this, okay, you are able to capture. But if the boundary layer is less than the first grid point over along y-axis, then you are not able to capture the boundary layer and it will escape. So the meaning is you will be not getting the data of the boundary layer. So it is not advisable for us. So the main important thing what we need to calculate is the y place. So basically the non-dimensional distance along y. So the meaning is, so what should be the first grid point? What is the spacing, or what, at what distance the first grid point has to be spaced? Okay, so that you can capture the boundary layer. So that is nothing but y plus. You have x plus also, you have z plus also. So if it is like along x direction, you have x plus. If it is along y direction, it's called y plus. If it is along z direction, it's called z plus. Okay, so what is the first grid point placed near to the wall? Okay, so that is nothing but you have the non-dimensional distance. So it's nothing but y plus. Okay, so where should be placing the first grid point is very very important, so that we can capture the boundary layer phenomena. Okay, so y plus calculators are available, so it is very very important to first calculate the y plus, then go for the spacing of the grid points. Okay, so I already told you, for not all aspects you use uniform grid. For some aspects, so here you can see it's not uniform grid, because we are interested near to the wall, so there should be very very finer mesh to capture the data. Okay, so here let's see types of the fluid approach. So you have two different kinds. One is like finite control volume approach. Next, other one is infinitesimal fluid element approach actually. Okay, so you have a control volume approach, and you have infinitesimal fluid element approach actually. Okay, so what is the difference we'll be seeing? So here the control volume is nothing but an entity where it is drawn in a space. Okay, so this is an entity. So this control volume can be any shape. It can be a square, rectangle, arbitrary shape. So control volume is an entity where we are interested to see the effects of fluid phenomena which is passing through it and accumulated in it and going out of the control volume. Okay, so our area interest is confined to this particular type of volume or this entity. So what we do is like, you will draw the control volume. So control volume can be an arbitrary shape, any shape actually. It is not fixed that you can have a control volume like this also, or you can have a control volume like this also. So depending upon the domain that you have, depending upon your interest, your geometry or area, so you will have this thing. Okay, so let's say if you are doing flow over a circular pipe, let's say flow through the circular pipe. So then, so here the control volume, since we are taking internal flow, the control volume, whatever we have, it's like circular thing. Okay, so here if you see 2D section, it is circular cross section. So how the flow is going inward and outward. So flow crossing per unit area is called flux. So the flux inwards and flux outwards has to be calculated. And what is the amount of fluid that is accumulated inside the this finite control volume has to be seen actually. So what are the effects that happening when the fluid is passing or entering and accumulated and leaving the control volume has to be put in the mathematical form. Okay, so this is what we have. And here in the finite control volume also, so you have two kinds. Okay, so one kind is like, this finite control volume is fixed in space. So fixed in the space in the sense, so this control volume will not move, so it will remain stationary. So the velocity of the control volume, so V of Cv will be equal to 0. So the velocity of the control volume is 0 in the sense the control volume is fixed in space and the fluid is moving through it. Okay, so that is the meaning of finite control volume fixed in space with the moving fluid moving through it. Okay, and here the second kind of approach is nothing but the finite control volume moving with the fluid such that same number of fluid particles will be accumulated inside the control volume. So here the meaning is, so let's say the fluid velocity V is nothing but V fluid. So let's say it is 2 meter per second. Okay, so if the control volume is moving with the fluid, let's say what is the approach is, so even the control volume Vc, we will have the same 2 meter per second. So in this phenomena, what is happening is, at all the times you will have same number of fluid particles which is accumulated inside the control volume, and it will be traveled along with the fluid. Okay, same number of fluid particles or the same fluid particles will always present in the same control volume. Okay, So here the control volume, when it is moving with the fluid, it can change its shape. Okay, so but whereas the control volume, it is fixed in this space, it cannot change its shape. Okay, so for example, the fixed control volume kind of thing, you can take the flow through pipe. So this is what we have. Okay, so what is happening here? So the control volume is an entity where you will be seeing the fluid flow phenomena which is passing inside it and accumulated inside it and going outward. So the boundary, so the surface enclosed this control volume is nothing but control surface. Okay, so the difference what we have in these two phenomena, let's say this is 1 and this is 2. So for the first approach, so basically you will derive the integral form of governing equations. Okay, so the integral form of governing equations, so the integral form of continuity equations that you will be deriving. Okay, so this thing, the first approach or the second approach what we have, you will be deriving integral form of governing equations, but there is a difference. So the first approach, we get a conservative form of governing equations. Okay, the meaning what we have is like here first and second approach are different. One is control volume fixed in space, the other one is control volume moving with the space. The governing equations derived in the first form is integral form, so we'll integrate everything through the control volume, and we will get what is the velocity, what is the pressure, what is the temperature. Okay, so the control volume approach will get an integral form of governing equations. We will derive integral form of governing equations, but here if the control volume is fixed in space, you will get a conservative form of governing equations. If the control volume is moving with the space, you will derive non-conservative form of governing equations. Okay, that is the difference. Here you can see 3 and 4. So third one and fourth one is the same, infinitesimal fluid element approach. So the third one is what we have is the fluid element is fixed in space. So here you can see is the molecules actually. It's about the molecular phenomena what we have, and here you can see the fluid element is moving with the flow. Okay, so in this approach, third and fourth approach, the difference is like you will derive a differential form of governing equations. Okay, so the first approach for the first and second approaches, for the control volume approach, you will derive integral form of governing equations, and for the third and fourth approach, you will be deriving differential form of governing equations. Okay, so even for the third and fourth approaches, what the difference is? So here the fluid element is fixed in space. Here the fluid element is moving with the fluid. Okay, so fluid element fixed in the space in the sense like here you will derive a conservative form of governing equations. So here you will be deriving a non-conservative form of governing equations. So you can see the conservative form or else non-conservative form of governing equations, but the physics of the fluid does not change, or the value like whatever the phenomena that we need to calculate will not change. Okay, these are different forms. Fine. So with this background, now let's see. So what is the major difference that we have in finite volume approach and finite difference approach? Okay, so this is very important. In CFD, you have two different types of approaches. So one is called FDM, other one is called FEM. Sorry, FVM. So we will see. So you have FDM and you have FVM. So these two are the important approaches that will be seen for the CFD. So we will see in detail about these approaches in further modules. Okay, but let's introduce what are the major differences between the finite difference method and finite volume method. Okay, so let's take the example of flow through pipe. Okay, So you have a rectangular cross-section pipe, let's say. Okay. So if you have a rectangular cross-section pipe, let's say this is the cross-section. So if you want to know the velocity at different points, so if you want to know the velocity at the different points inside at different cross-sections, let's say I'm talking about this one. So let's say this is our pipe. Okay. So of length L. Okay. This is the hydraulic diameter D, let's say. Okay. So at each and every cross section for a fully developed flow, you need to calculate what is the velocity. Okay. So what is the pressure? That thing has to be seen, estimated. So let's say if you want to estimate for this kind of problem, what are the flow parameters? We take an approach called finite difference method. So we will see what is it. Now, as I told you, so the example what we have taken is an internal flow. If the flow is internal, you need to perform mesh inside the domain actually. If the flow is external, so let's say this is flow over flat plate, you need to perform the mesh over the object. So here, since the flow is internal flow, you have to perform mesh inside the object actually. Okay. So if you see the cross section, so that is rectangular face. So let's see the mesh here. Okay. So this is what we have. Okay. So this is the cross section that we have. So as I told you, so what are these? So let's take the axis also. This is y axis and this is the x axis and this is origin. Okay. So this is of unit length 1 and this is of unit length 1. Let's take. Okay. So as I told you, the intersection of x lines and y lines will give you grid points. So this is one set of grid point. This is grid point. So yeah. So basically these are grid points. Okay. So here there is one more aspect. So this thing. So these points. So let's say this is 1, 2, 3 and 4. So we have 4 boundaries. So basically these are called boundary nodes or the boundary points. Okay. And the remaining points which you have here 1, 2, 3, 4, 5, 6, 7, 8, 9. So these 9 points are called the internal points actually. Okay. So are the interior points. You have the boundary points and you have the interior points. Okay. So we will see basically what is this boundary points and so what is this interior points. So what we will be doing in the finite difference method, we'll be seeing. Okay. So let's consider once again this square section. This is the mesh. So this is the mesh we have. So if you want to calculate, let's say the velocity at this grid point. Okay. So we need to actually name indexes. So here in the finite difference method, so you have index notation. You have I, which is called along x direction index notation, and you have j, which is called y direction index notation. So this point we call it as I comma j. Okay. So what would be this point? So this one would be I minus 1 comma j. So what would be this point? This one would be I plus 1 comma j. Okay. So this is index notation actually. Similar to like x and y axis, whatever we have. So let's if you take this is x comma y. So this is x plus 1 comma y. This is x minus 1 comma y. So we can relate actually. So what we have is like I comma j. So which is similar to x comma y. So I minus 1 comma j. So which can relate like x minus 1 comma y. So I plus 1 comma j. So which you can write as x plus 1 comma y. So you can relate in this way. Fine. So and here what we have is like one more point. So this is called I comma j plus 1, and this is called I comma j minus 1. Okay. So why we have taken these 4 points? Because so this area of interest or the point of interest is depending upon all these 4 points. So let's take this is point, this is 1, and this is 2, and this is 3, and this is 4. Okay. So this node which is I comma j is surrounded by neighboring 4 nodes. Node 1, 2, 3 and 4. Okay. So what we do in finite difference method is we will solve the conservative form of equations at this grid points. Okay. So what, let's say you have continuity equation. So let us consider continuity equation. So of 2 du by dx plus dv by dy is equal to 0. So if you want to perform this finite difference approach at this particular grid point, so what we have is like if you have a forward difference method, so we will see what is in detail for what is forward difference, what is central difference, what is backward difference. Okay. So here in today's session we are just seeing what is the difference between finite difference and finite volume approach. So in the finite difference method, so now how we actually replace this partial derivative in the form of algebraic equation we will be seeing actually. So let's consider you have a partial derivative here. So we are taking a forward difference method. So don't worry, in detail, like we will be seeing what is forward difference method, like how we had obtained that expression we will be seeing. So the simple thing, so du by dx can be written as, so u of I plus 1. So let's take it as u2. So u2 minus u1 by delta x. Let's take this one. Plus v2 minus v1 by delta y is equal to 0. So what we are doing is like we can actually write what is this u2. So the u2 phenomena, if you write index notation, so u of I plus 1 comma j minus u of I comma j divided by delta x. Okay. So plus v of I comma j plus 1 minus v of I comma j divided by delta y is equal to 0. Okay. So this is how we write for a finite difference method. So this is called a forward difference method in the finite difference method. Okay. So we'll see in detail what is the forward difference approach, what is the backward difference approach in detail in the further class. But meanwhile, so for the forward difference approach, you will take like u2 minus u1 by delta x. So that is what we take. So here, what we have taken. So let's take the x is equal to or I is equal to 1. If I is equal to 1, what happens? So this will be u2. So I is equal to 1 and j is equal to 1. It is like u of 1 comma 1. So what happens like here u2, when I is equal to 1 it would be u2. Here I is equal to 1, this would be u1. Okay, this is what we have. So if you rewrite this form, you will get a linear form of equations. Okay. Similarly, you will actually write for each and every grid point. So in order to get so you should get the value of u of I1 also. So initially you will get what is u of I plus j. Okay. So through using initial conditions or using some approximations, you'll calculate those values. You'll get those values, guess and calculate in an iterative method. Now what we do in finite difference approach is whatever the partial derivative terms we have, so we will actually replace this in the linear algebraic form at grid points. Okay, so at particular grid points. Fine. This is the finite difference method. So now we will be seeing what is finite volume method. In CFD, so basically whatever the phenomena we have, so whether it is a finite difference method or the finite volume method, so we need to actually replace these partial derivative terms in the form of algebraic expression, okay, to solve in a matrix form. So for the finite volume approach, so let's take an example of flow through a rectangular cross section pipe. Okay, let's take, this is what we have. Okay, flow is going through the rectangular cross section pipe. Fine. So this is what we have. So in the finite volume approach, so basically we will derive these governing equations at the center of the cells. So let's take, so the cross section of this pipe, triangular cross section pipe. So what we have done? So we have done, it's like you have triangle 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's say you have 9 triangles. So what we have done is like in the finite volume method, so depending upon the phenomena. So here actually what we have taken is like unstructured grid. Okay. So in the finite volume approach, so we will derive these governing equations, we will actually discretize the governing equations at the center of the cell or the center of the cell. So for the finite difference method, so what we have is like, so we will derive this governing, derive the discretized equations at the node points. Here these are the node points. So in the finite volume approach, we will derive the discretized equations at the center of the cell. For the finite difference method, we will derive these discretized equations at the grid points. Okay, so that is the major difference between the finite difference method and finite volume method. Okay, so there are some advantages and disadvantages in both the methods. So finite difference method cannot be actually you cannot be used for complex geometries or for irregular geometries. It cannot adopt any shape. Let's say you have a geometry like this or something clumsy like this. So for this sort of geometry kind of thing, so the structured mesh entity would actually result some problem. So why? Because so what happens when you take very curved objects is like, so let's say you have lines which are going along x-axis, along lines going along y-axis. For the curved object or for irregular objects, when you're trying to perform a structured mesh, so this x lines will try to meet somewhere, some point, and form a negative volumes, and even y lines will meet somewhere, some point, and form a negative volumes. Okay, so this is the problem that we face when you apply finite difference approach for complex geometries. Okay, so the best method available is finite volume method. So finite volume method can be applicable for all type of geometries. So there is no restriction for the finite volume method. So what we do is like, so we divide say into structured or unstructured mesh, and we apply the conservative form of equations that is at the center of the cell. Okay, so this is the approach what we see in the finite volume method. So it is very advantageous for any complex geometry, and the process is somewhat complicated when you compare with finite difference method, but finite volume method is applicable for all the type of problems. It is not restricted for any other geometry, but finite difference method is restricted to some particular type of regular objects only. When you go to the complexity levels, so the finite difference method will have some drawbacks, but finite volume method ensures that the conservativeness is holded, and the numerical approach is very okay confined in the boundaries. Confined in the sense, like you have the conservativeness. So whatever the flow that is going, it will come out. So at each internal fluxes at each cell phases would get cancelled. So we will see. So what is these things in detail when we talk in detail about finite volume and in detail about finite difference. At the end, we will compare what is the difference, major difference between finite volume and finite difference method. Okay, so here I'm just giving the glance. So what is done for the finite difference method and finite volume method. So the in general, in summary, what we have is for finite difference method, you will solve the governing equations at the grid points. For the finite volume method, you will solve the governing equations at the centroid of the cell. Okay, and what we do in the both the approaches is the same. So we will actually convert the partial derivative terms to the algebraic terms. Okay, so in the finite volume approach, let's say if you have a dou square w by dou x term. Okay, so this term we have, let's say what we do is like, so we will take in this form. So okay, so this is written in the form of vector notation. So this term can be expressed in this way. Okay, so you can actually, so what we do is like surface integral. Actually, we will perform the surface integral over this surface from the Gauss theorem. So you can actually relate, or you can actually change this surface integral to line integral. So what we write is like line integral. Okay, like n dot gradient actually. Okay, and dl. So let's say, so basically this in this form it is changed, and you will calculate the fluxes along these boundaries and try to interpret. So these things we'll be seeing in detail in the finite volume method when we see, okay, in the further modules. So here what we have done is like we will be getting again same. So the n is nothing but normal vector, which is nothing but nx of I cap plus ny of j cap, and you know what is del. Delta is nothing but dou by dou x of I cap plus dou by dou y of if it is like z axis and z of k cap. So plus this is j cap plus dou by dou z of k cap. Okay, so if you substitute these forms, then you will be getting this entity, and you will have the gradient calculated at each phases, and the same approach can be done again. Okay, so here the finite volume method is one sort of approach of for discretizing the governing equation into linear form, and difference method is at the grid point. Okay, so in next module we'll be seeing in detail, so what is finite difference method, so how we had got this expression u2 minus u1 by delta x, or u of I plus 1 comma j minus u of I comma j by delta x, what is forward difference method, what is backward difference method, what is central difference, how we get this formula, what are the advantages, what are the disadvantages of finite difference method. Okay, what are the lower order schemes, higher order schemes. Okay, we'll take some tutorial, and then we'll go to the finite volume method. Okay, so thank you.
Like, share and subscribe. Hit the bell icon for more updates.